Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams. Having looked at formula mass or relative molecular mass and percentage composition, it is now time to move into empirical formula and molecular formula, as of course this also covers some of the questions you might likely get in your UTME exam. So very quickly, let's get into it. When we say empirical formula is the formula of a compound which shows the simplest mole ratio. Emphasis on the word simplest mole ratio of the elements that make up 1 mole of that compound. Let me give examples for that. Take for instance, let's say glucose 6 is H12O6. Now the smallest mole here, if you look through, you see that it is possible I get through dividing by 6. 6 in C6, that will give me C. 6 in 12 here, that will give me 2. 6 in oxygen here, that's going to give me 1 as well. This simplest mole ratio here, this CH2O, is what we call empirical formula, whereas the actual number of atoms of elements present in 1 mole of a compound or a molecule is what we call the molecular formula. You can see the molecular formula is the formula of a compound which shows the actual number of moles of the different elements which make up 1 mole of a compound. Invariably, since I divided through by 6 here, from here we can actually, if I decide to get the CH2O back to the molecular formula that I have, it simply means I can multiply through by 6. And when I multiply through by 6, I'm going to get C6 H12O6. Of course, from this, I can actually bring out the formula. Actually, what we have here is empirical formula multiplied by a certain number that goes through in all of the elements that makes up this compound. Let's represent that as N. Empirical formula times N equals to, this is the molecular formula. We only need to get the molecular mass here. And with this formula, when we say empirical formula times a certain number that goes in the compound, that divides through in the compound, equals to the molecular mass, mm. We can actually do a lot of things which we are going to apply much later. But the important thing is that when we talk empirical formula, it is the simplest mole ratio of the elements which make up a compound, and molecular formula of a compound is the actual number of moles of the elements which make up 1 mole of that compound. What we will be doing is, of course, to calculate, to have calculations that helps us find our empirical formula and our molecular formula. Don't forget, I said empirical formula times a certain number which divides through in the molecular formula is equal to the molecular mass. We will apply this much later. Now, moving on, how do we calculate empirical formula? What are we expected to do? These are the things we are expected to do. The first thing is that the composition of the compound that we are going to be given in the question, talking about the data we are going to have in the question, in terms of what that compound is composed of, they should give us at least in the percentage by mass of each element present in that compound. Like, I should be told, okay, this is given the percentage of carbon, percentage of hydrogen, percentage of oxygen, or I should be given the mass of each element present in a fixed mass of the compound. Take for instance, if you say 2 grams of carbon is present in 10 grams of glucose, or you say 3 grams of hydrogen is present in 1 gram of glucose. So that's what I mean by mass of each element in a fixed mass of the compound. If after having either of A or B, The next thing is for me to convert what I have here into mole. And how do I convert to mole? I do that by saying the mass, the percentage by mass that I have divided by the molar mass. Recall that mole equals to mass over molar mass. And after I must have gotten the mole of the various elements that make up the compound, I have to get the moles of the elements in the ratio. Let's say like here, this is 1 to 2 to 1. That is it. 1 to 2 to 1. Then after that, if I have my ratio there in decimal, I have to convert to the simplest whole number ratio. I have to multiply through by a certain number that just converts it into whole number. So what we're going to do right about now is to have questions so that we can quickly solve things, and you see how we apply steps 1, 2, and step 3. And of course, we're going to take a number of JAM or UTME questions. Moving on, we have some set of questions to buttress what we've been saying, and it's about calculation of the empirical formula. Look at the first question. It says a compound contains 28.6% magnesium. So what we do there is, okay, this is magnesium, we're talking carbon, and then we're talking oxygen. From the question, what we have, the percentage by mass of carbon of magnesium present is 28.6%. The percentage by mass of carbon present is 14.3%. And then the percentage of oxygen present is 57.1%. Yes, at the end of the question, we were supposed to be given, okay, magnesium, the atomic mass of magnesium is 24, that of carbon is 12, and that of oxygen is 16. So having this, the next thing for us to do is to change to mole. And how do we do that? The percentage by mass divided by the atomic mass. So this is 28.6 divided by 24, 14.3 divided by 12, and 57.1 divided by 16. So if we compute from our calculator, what we are going to have is 28.6 divided by 24, 1.19, 14.3 divided by 12, 1.19, 57.1 divided by 16, 3.57. Of course, when I listed the steps we need to take for calculating our empirical formula, after adding this, I told us that we are going to express in the smallest ratio possible. So what we then do is to divide through by smallest ratio. Dividing through by smallest ratio, when you look at this, is all 1.19. So 1.19 divided by 1.19, 1.19 divided by 1.19, 3.57 divided by 1.19. When we look at this, this will give us 1, this will give us 1, and this will give us 3. Yes. So moving on with this, magnesium is occurring one time. Magnesium, carbon, O3. So this is magnesium triosocarbonate 4. This is my empirical formula. So it is very simple. Convert to mole, divide by the smallest mole ratio, and whatever you get, that is your empirical formula. That's question 1. Moving on to question 2, we basically have 5.24 gram of a compound containing 1.06 gram aluminum and 4.18 gram of chlorine. Calculate its empirical formula. Now, in analyzing this, this is the same compound, so it's more like we have 5.24 gram of a compound, and this compound contains 1.06 gram aluminum, and it contains 4.18 gram of chlorine. Of course, it is the same compound. So when it is the same compound, what we can just do is straight away move into calculating for the mole. Aluminum chlorine. In the case of aluminum, we have 1.06 gram. Recall that for mole, It is mass over molar mass, or the atomic mass in this case. So 1.06 divided by 27. We can use that straight away because the component elements are in the same compound. So for chlorine is going to be 4.18 divided by 35.5. We compute that from our calculator. We get 0.04 and 0.117 mole. Now that we have the mole, the next thing is for us to divide by the smallest mole ratio. In this case, 0.04 divided by 0.04, 0.117 divided by 0.04. So looking at this, it means my aluminum is happening once and my chlorine is happening twice. So that is aluminum chloride. Take note, it is happening in the same compound. These components are in the same compound. That is why I can directly look for the mole. I can directly look for the mole. Yes, and this will be my mole ratio. Mole ratio. Yes, this will be my mole ratio. I have looked for the mole here by saying mass over molar mass, mass over molar mass. So I can conveniently look for the mole ratio. So this is what I get, and that is aluminum chloride. That is the empirical formula. Good enough. The empirical formula in this case is also equal to the molecular formula, because normally this is what aluminum chloride looks like. So I am saying in some cases empirical formula can be the same as your molecular formula in some cases. So that ends question 2. Emphasis on the word this component element, this constituent element are present in the same compound. So when they are in the same compound, I'll directly look for the mole. But when on analyzing, we find that those constituent elements are in different compound. We cannot look for the mole directly. We first of all have to look for the percentage composition, as we will see in question 3. So moving on to question 3, a compound on analysis gave the following results: 0.60 gram carbon in 1.50 gram of the compound, 0.12 gram hydrogen in 1.80 gram of the compound, 1.28 gram of oxygen in 2.40 gram of the compound. Calculate the empirical formula. And this is exactly what I am saying. The constituent elements are present in different mass of the compound, so we have to analyze this. Unlike for question 2, the constituents are present in the same compound. So how do we go about this? We first of all have to look for the percentage by mass of each of the constituents. So in the case of carbon here, the percentage of carbon here is actually 0.60 out of 1.50 times 100. That of hydrogen, percentage of hydrogen, that is going to be 0.12 out of 1.80 times 100. And that of oxygen, that is 1.28 out of 2.40 times 100. That way we get the percentage by mass of the respective elements. So computing this, I'm going to get 40% for carbon. The percentage by mass of hydrogen will be 6.67%. The percentage by mass of oxygen will be 53.33%. Having analyzed this, I can then proceed to look for my empirical formula. This is carbon, this is hydrogen, this is oxygen. Okay, the percentage by mass of this is 40%. The percentage by mass of hydrogen is 6.67%. The percentage by mass of oxygen is 53.33%. So I'm going to convert to mole. That's 40 divided by carbon is 12. At the end of the question, we were supposed to be given carbon equals to 12, hydrogen equals to 1, and oxygen equals to 16. Those are the atomic masses, okay? 6.67 divided by 1 and 53.33 divided by 16. If we try to then we compute this from our calculator to get the mole ratio. So computing from my calculator, I'm going to get 3.33 mole, 6.67 mole, and 3.33 mole. So looking for the mole ratio, we are going to divide through by the smallest mole here. So that will be 3.33 divided by 3.33, 6.67 divided by 3.33, 3.33 divided by 3.33, because if you look through the mole, so this is mole ratio. If you look through the mole, 3.33 is the smallest, so this will be 1 to 2 to 1, 1 to 2 to 1, and in computing this, so that is CH2O. CH2O, that is what we have, CH2O. So my empirical formula is CH2O. Yes, it doesn't end there, but the important thing to note for this question is that depending on what you're given, if the respective masses of the constituent element are present in different masses of compound, then you have to analyze and first of all get the percentage by mass of the element before you proceed to find your empirical formula. Okay, moving on with the question 3, it says, and we should find the empirical formula and the molecular formula if the relative molecular mass is 60. So the empirical formula is CH2O, and here we were told to calculate also the molecular formula if the relative molecular mass is 60. So molecular formula is your empirical formula times n. But to get a certain number that cuts through the empirical formula, you use empirical formula times n equals to the molecular mass. These two formulas are very important. So in this case, we have CH2O times n. The molecular mass as given in the question is 60. So what is my carbon? Normally at the end of the question, we've been given that carbon equals to 12, hydrogen equals to 1, and oxygen equals to 16. Okay, carbon is 12, hydrogen is 1, 1 times 2, 2, oxygen is 16. So that 12 plus 2 plus 16 is 30. 30 times n, 30n equals to 60, okay? Equals to 60. So that my n equals to 60 over 30. Therefore, my n equals to 2. Now that my n is 2, I can now come here. What is my molecular formula going to be? My molecular formula is going to be CH2O times my n, which is 2. So that's going to give me C2H4O2. This is my molecular formula. Look at it very well. My molecular formula is empirical formula times n, but I don't know what my n is. So therefore, I'm going to say empirical formula times n. Empirical formula times n equals to empirical formula times n equals to the molecular mass. I'm going to put the empirical formula here, CH2O, like we got here. CH2O, that will be 12, 1 times 2, 2, 16. Add it together, that is 30. That way I was able to calculate for my n. Now that I have my n, molecular formula, that is the formula of 1 mole of the compound, is going to be 2 times C, C2, 2 times 2, 4. 2 oxygen, and that means my molecular formula is C2H4O2. Let's moving on, still on empirical formula, let's really talk about oxidation states. There are some elements that have more than one combining power. Take for example, sometimes you could have copper as having oxidation state of +1. Sometimes you can have it as having oxidation state of +2. In this case, if copper were to combine with chloride, for example, here you're going to have it as CuCl. Of course, you recall that chlorine is having a -1. But in the case of this, I'm going to need 2 chlorine here, copper 2 chloride. This is copper 1 chloride. This is copper 2 chloride. It's the same in the case of iron. Let's say Fe2 plus, Fe3 plus. This is iron 2 ion. This is iron 3 ion. In the case of combining with chlorine here, this is going to be FeCl2. This is iron 2 chloride. This is going to be FeCl3 because chlorine is a -1 and this is 3 plus. Then I'll need 3 chlorine to combine with that ion. This is iron 3 chloride. So some elements have more than one combining power, hence they can form more than one compound containing same element but in different proportions. We do have empirical formula questions that relate to this element with variable oxidation state. One of such, to buttress what I'm trying to say here, is this question that says a copper forms 2 chlorides. One of the chlorides contains 36% of chlorine, the other 53% of chlorine. Calculate the formula of the 2 chlorides and name them. So in this case, how are we going to, it is still empirical formula. So how do we go about things? You say chloride A, chloride B. Okay, this is question A. Chloride A, chloride B. We were told that forms 2 chloride. One contains 36% chlorine. In chloride A, if the chlorine content here is the chlorine here is 36%. The chlorine here is 36%, but we're talking copper here. That means the copper in this case, if we say 100 minus 36, that's going to be 64%. In the case of chloride B, we said the other 53% chlorine. Chlorine here is 53%. That means the copper here is going to be 100 minus 53, that's going to be 47%. So what we then do is that we are going to quickly convert to mole. Our copper is actually 64. Copper is 64. At the end of the question, we will have it that Cu equals to 64, while our chlorine equals to 35.5. Of course, this is going to be 64 divided by 64, and this is going to be 36 divided by 35.5. In the case of this is going to be 47 divided by 64, and this is going to be 53 divided by 35.5. So if we compute, this will give me 1, this will give me 1. So what that means here is that the copper is happening one time, CuCl, and therefore this is copper 1 chloride. This is copper 1 chloride because this is copper 1 chloride. Reason being that I'm going to have only one chlorine combining with this copper, and that is telling me that this copper is more like Cu plus. Okay, if I come here, okay, computing from my calculator, this is going to give me 0.73, and this is going to give me 1.49. Of course, in this case, I'm going to have to divide with the smallest mole ratios. This is 0.73 divided by 0.73, 1.49 divided by 0.73. This will be 1, and this is going to be 2. So in this case, this is copper 2 chloride, CuCl2, copper 2 chloride, and this is copper 1 chloride and copper 2 chloride. That is the formula of the 2 chlorides. Look at it very well. You are given 2 chloride, so that gives me copper 2 chloride. The copper is 1, the chlorine is 2. If I'm to name that, that is copper 2 chloride. So that ends that. Just look at it very well. Copper forms 2 chloride. One contains 36% chlorine. If it contains 36% chlorine, then what is the other percentage that makes it 100? That means 64% is for the copper. The other 53% chlorine. If I have 53% chlorine in the other chloride, that means the copper is now going to be 100 minus 53, 47% for the copper, percentage of copper in there. So that ends that ends question A. Moving on to question B, we were told that an oxide of metal X whose relative atomic mass was 65. So which means we have a metal X, relative atomic mass was 65. Metal X, relative atomic mass was 65, was reduced to the metal. So in other words, we have, let's say, an oxide X. Now this was reduced to the metal so that we have only X. Removal of oxygen is reduction. Actually, loss of oxygen from a substance is actually reduction. Okay, metal to the metal was reduced to the metal. 1.62 gram of the oxide formed 1.30 gram of the metal. So which means we have 1.62 gram of the oxide, and it gives us 1.30 gram of the metal. Calculate the empirical formula. So if X is 1.30, so the question is, if my X is if X, metal X, let me put the metal first. If metal X is 1.30, then it means my oxygen there is going to be 1.62 minus 1.30, and that is going to give me 0.32. Normally oxygen is 16 and hydrogen is 1. Normally oxygen is 16, and I've been given the metal X to have relative atomic mass of 65. So that what that means is that by the time I divide it by 65, that means I'm converting to mole, as this is mass over the relative atomic mass, and 0.32 for my oxygen, that is going to be divided by 16. 1.30 divided by 65 is 0.02. 0.32 divided by 16 is 0.02. So they are the same. So dividing by smallest ratio here is going to be 0.02 divided by 0.02, 0.02 divided by 0.02. So this is going to be 1 to 1. So having 1 to 1, that means my X is 1 and my oxygen is 1. The meaning is XO is the empirical formula of the oxide. Look at it very well. We have a metal X whose relative atomic mass was 65, and it was reduced to the metal. To reduce it to the metal means we are removing oxygen from the oxide so that we have the metal left. And on analysis, it formed 1.62 gram of that oxide formed 1.30 gram of the metal. So if out of this 1.62, if out of this 1.62, 1.30 was the metal, then it means that 1.62 take away 1.30 is going to give me the mass of the oxygen contents there. So 1.62 minus 1.30 gives me 0.32. What I'll then do is convert to mole, mass over molar mass, over, in this case, the relative atomic mass. So 1.30 divided by 65, 0.02. Oxygen, which is 0.32 now from calculation, divided by 16, 0.02. Of course, divided by our smallest mole so that we get the ratio of the atom. 0.02 divided by 0.02, we get 1. So the formula of the oxide is XO. Now moving on to question C, iron forms 2 chlorides, 56 containing 56% and 65% chlorine. Calculate the formula and give the names of the chloride. So they're talking about iron, Fe in this case, forms 2 chloride. Okay, let's say, okay, chloride A. This is for question C. Chloride A, chloride B. In this case, we have iron there. Metals should always come first. And then we have chlorine here. For the first one, containing 56% chlorine. So if the chlorine is 56%, so the ion in the first chloride is going to be 100, take away 56, and that is going to be 44. So normally at the end of the question, we were supposed to be given ion is 56 and chlorine is 35.5. 5.5. So in this case, iron is now 44, so that's going to be 44 if I'm to convert this to more over 56, and this is going to be 56 divided by 35.5. In the case of chloride B, chlorine was 65%, so the chlorine and then the iron. Okay, if the chlorine was 65%, then the ion is going to be 35%. So for me to convert this will be 35 divided by 56, and then 65 divided by 35.5, which is the atomic mass of chlorine. So this is what I am going to try to compute. By 56 gives me 0.79. 56 divided by 35.5 gives me 1.57. Okay, when I look for the ratio, then that will be 0.79 divided by 0.79, 1.57 divided by 0.79. This will give me 1, and this is going to give me 2. So then this is FeCl2. But we're told to give the names of the chloride. FeCl2, that is iron 2 chloride. Iron 2 chloride. Now moving on to this, 0.625 divided by the smallest ratio, 0.625 divided by 0.625, as that's the smallest ratio, this will give me 1.83 divided by 0.625, approximately 3. So the implication of that, this is going to give me 1, this will give me 3. The implication of that is iron is 1 and chlorine is 3. That is FeCl3. In that case, this means iron 3 chloride. So that just answers that. Is all about analysis. Moving on to question D, which is the last question before we then move into solving UTME, questions that relate to UTME. 3 oxides of nitrogen. So we basically have 3 oxides of nitrogen. And I'm talking oxides of nitrogen, we're looking at them like NO, NO2, maybe N2O and stuffs like that. But for now, we don't know what it's going to be. So 3 oxides of nitrogen contain 36%, 53%, and 70% oxygen. So I'm going to say 3 oxides. Let this be oxide A, oxide B, and then oxide C. So analyzing oxide A, it contains 36% oxygen. So the oxygen here is 36%, and then it means that the nitrogen here then is going to be 64%. For oxide B, 53% oxygen it contains. Oxygen was 53%. Then it means the nitrogen content there, it means the nitrogen content here is going to be 47% if we subtract 53 from 100. And then for the third oxide, oxide C, the nitrogen, the oxygen here was 70%. And then the nitrogen is therefore going to be 30%. At the end of the question, we must have been given that oxygen is 16, oxygen is having relative atomic mass of 16, and nitrogen is having relative atomic mass of 14. We must have been given at the end of the question. So that this means 64 divided by 14. So that this means 64 divided by 14, 36 divided by 16. Looking at oxide A, 64 divided by 14 is 4.57, 36 divided by 16 is 2.25. Of course, we are going to have to divide by the smallest ratio here. So this is 4.57 divided by 2.25. This is the smallest mole. So this is 2.25 divided by 2.25. So this is going to be 2, approximately 2, and this here is going to be 1. The implication of this is my nitrogen is 2, N2O. That is the implication. Calculate the formula of the oxide. So the formula of this is N2O. If I come to oxide B, 47 divided by 14 will give me 3.56. 53 divided by 16 will give me 3.31. The implication of that, if I divide by the smallest ratio, divided by 3.31, this is all, if you divide, this is all approximately 1 to 1. So 1 nitrogen, 1 oxygen, that is what? NO. That is the formula for oxide B. For oxide C, so we then have to divide by the smallest ratio. Here, this is the smallest ratio. So that is 2.14 divided by 2.14. 4.38 divided by 2.14. This here will give me 1, this here will give me 2. So that the implication of this is that this is NO2, nitrogen 4 oxide. So you can see these are the various formulas of the oxides, and these are things we can expect from UTME. It's all about flowing with things, percentage by mass, converting to mole, getting the smallest mole ratio, and getting the formula of your compound. Let's now move into quickly solving questions that are UTME related. Moving on and taking JAM questions that are related to empirical and molecular formula. The first question you're going to see is 1985 question 3. It says an organic compound contains, as you can see on your screen, 72% carbon. We have carbon and then we have hydrogen. 72% carbon, 70% carbon, 12% hydrogen, and 16% oxygen. 12% hydrogen and 16% oxygen. Okay. Looking at this, converting this to mole, this will be 72 divided by 12, and this will be 12 divided by 1 because hydrogen is 1. You can see that at the end of the question, we were given the relative atomic masses of the constituent element, and then 16 divided by 16. 72 divided by 12, that is going to be 6. 12 divided by 1, 12. 16 divided by 16, 1. So now that we have this, the next thing is to divide by the smallest ratio. 1 is the smallest ratio, so that will be 6 divided by 1, 12 divided by 1, 1 divided by 1. You still end up with 6, 12, and O. So the empirical formula here is going to be C6H12 and O. If we look at the options there very well, that is option D. That's 1985 question 3. You have to be fast about it, and you have to work with precision. Option D. Option D. That is the answer. Option D. (1992) question 48. As you can see displaying on your screen, it says an organic compound has 40.1% carbon. Carbon is 40.1%, and hydrogen was 6.667%. Hydrogen was 6.667%. This and this, if you add together, is not yet up to 100, and then they deliberately refuse to talk about oxygen here. And yet, fine, for an organic compound, it can be made up of carbon and hydrogen only. But in this case, when you add this and this, it is not up to 100. So that tells you that the third component or constituent is going to be oxygen. And if you look at the options, they wanted the empirical formula of a compound that has carbon, hydrogen, and oxygen. So on your own, you have to look for what is the percentage of the oxygen. So that is going to be 100%, take away 40.1 and take away 6.667. So for oxygen, that is going to be 100, take away 40.1 and take away 6.667%. So this will give you 53.233%. That is the percentage of oxygen. So for carbon, carbon is going to be 40.1 divided by 12, 6.667 divided by 1, 53.233 divided by 16. So when we compute this, we're going to have 3.34, 6.67, 3.33. If we divide by the smallest mole, that's talking about looking for the mole ratio, that will be 3.34 divided by 3.33, 6.667 divided by 3.33, 3.33 divided by 3.33. This gives you 1, this gives you 2, and this gives you 1. So when you look at the C1, H2, and O1, so the empirical formula is CH2O, and if you look at that option, that is option C. Yes, moving on to the next question, 1997, question 39, as you can see on your screen. A sample of a substance containing only carbon and hydrogen burns in excess oxygen. So basically we have a sample, and this sample contains carbon and hydrogen. It then burns in excess oxygen. Okay, let me just separate that so that we have our sample. Okay, this is carbon and then this is oxygen. I'm going to have CO2. And in that question, if you look at it, it was said that if you look at that question, it was said it contains carbon and burns in excess oxygen to yield 4.4 gram of carbon dioxide. This is 4.4 gram of carbon dioxide, and then it contains hydrogen, and when it combines with oxygen, of course, it formed water or steam, as the case may be. In this case, this is 2.7 gram. Well, as far as stoichiometry is concerned, although that's going to be our next topic, you want to convert what you have here into mole, so that this means mass. Recall that our mole is mass over molar mass, so 4.4. If you calculate the molecular mass of carbon dioxide, that is 44. So 4.4 divided by 44, this is going to give you 0.10. This is going to give you 0.10 mole. 0.10 mole. And then looking at this, that's going to give you 0.10 mole. Looking at this, this is 2.7 divided by water is 18. 2.7 divided by 18. That's going to give you 0.15 mole. The implication of this is I could use this to get this, okay? In this case, 1 mole of carbon is equivalent to 1 mole of carbon dioxide. Therefore, mole of carbon, working with this. Therefore, mole of carbon is actually, this is 1, this is 1. 1 is equivalent to 1. So mole of carbon is actually 0.10 mole. And if we decide to convert that to mass, carbon is 12. As you can see, atomic mass of carbon is 12. So that is, if I want to get the mass of carbon, that is going to be mole times molar mass, and that is going to be 0.10 times 12, and that is going to be 1.2 gram. Now, working on hydrogen here, okay, this is 2 mole. 2 mole of water is 0.50. Then the hydrogen in itself is also 2 mole. So the implication of that is mole of hydrogen gas is also 0.15 mole. Yes, it's also 0.15 mole. Then if you are looking at converting this to mass of hydrogen is going to be mole times molar mass, and that's going to give us 0.15 times 1 times 2. In this case 1 times 2, because hydrogen is exists as diatomic. 1 times 2, that's 2, so this gives me 0.30 gram. So having 1.2 gram and having 0.30 gram, these are the two numbers I can then use to calculate my empirical formula. So moving on, I basically have carbon and then I have hydrogen. Okay, in the case of carbon, carbon was 1.2 and hydrogen was 0.30. Okay, 1.2 divided by 12, 0.30 divided by 1. So this will still give me 1.2 divided by 12. This is going to give me 0.10 mole, and this is going to give me 0.30. If we divide by the smallest mole ratio, this is 0.10 divided by 0.10. 0.30 divided by 0.30. This will give me 1. This will give me divided by 0.30 divided by 0.10. This will give me 3. So that means C and then H3. So that is the empirical formula for that question. Just mixing up stoichiometry with empirical formula there, and that ends that question. When you look at your option, the correct answer here is option A. The correct answer is option A. So moving on, we have another UTME question, 1999 question 5. The question says a gaseous metallic chloride MClX. So we basically have MClX, of course, consists of 20.22% by mass of M. So you're telling me here that M is 20.22%. Without being told, you should know that the chlorine is going to be 100 minus 20.22, and that is going to be 79.88%. Of course, moving on, what do they want? The formula of the chloride is what? Okay, that is very direct. At the end of the question, we were told that M is 27 and chlorine is 35.5. We were told that M is 27 and the chlorine is 35.5. So what that means is that we need to convert this to mole. Converting this to mole will be 20.22 divided by 27, and this will be 79.88 divided by 35.5. It will be 2.25. So we then divide by smallest mole ratio. So 0.75 divided by 0.75 equals to 2.25 divided by 0.75. So here is going to give me 1, here is going to give me 3. So the implication of that is M, then Cl3. This is the formula of the compound, and if you look at the option there, MCl3, that is exactly option C. That is option C, MCl3. UTME questions, as you can see on your screen, it says a compound contains 31.9% potassium. 31.9 potassium is 31.9% potassium, and my chlorine in this case is 28.93. 28.93, and then the rest was oxygen, but we were not told the percentage. So this is basically 100, take out 31.9 and take out 28.93. You compute your result. What are you going to get? 39.17%. So what we're then going to do is to convert to mole. This is 31.9 divided by 39. Potassium as given at the end of that question. Your potassium was given as 39. Chlorine, this is 28.93 divided by 35.5 and 39.17 divided by 16. You then compute. So we then look for the, this is the mole we are going to get. We then look for the mole ratio. So this is going to be, the smallest mole here is more like 0.81. So 0.82 divided by 0.81, 0.81 divided by 0.81, because this is the smallest, 2.45 divided by 0.81. This will give you approximately 1, this will give you 3. So the implication of that is this is KClO3, that is potassium triazochlorate 5. Potassium triazochlorate 5. So that is our empirical formula, and if you look at the option there, that is option A. So moving on, we have another question, this time 2003 question 47. We were told we have 40% carbon, 6.7% hydrogen, 53.3% oxygen, and we're given the molar mass of the compound. We're told to look for the empirical formula. Before we can do that, we need to first of all calculate the empirical formula. So to get the mole of this is going to be 40.0 divided by 12, 6.7 divided by 1, and then 53.3 divided by 16. 40 divided by 12, that is going to give you, that's going to give you 3.33, 6.7, that is 3.33. So 40 divided by 12, 3.33, 6.7 divided by 1, 6.7, and 53.3 divided by 16 is 3.33. Okay, let's get the ratio. 3.33 divided by 3.33. 3.33 here is the smallest ratio. So 6.7 divided by 3.33. 3.33 divided by 3.33. 1 to 2 to 1. So the empirical formula here is CH2O. That's the empirical formula. So in this case, we were told that the molar mass was 180, and therefore we should look for the molecular formula. This is very easy because empirical formula times N equals to the molecular mass. So what this means is the empirical formula is CH2O. CH2O, and that's the mass of the empirical formula now equals to the molecular mass. When you look at CH2, C here is 12, hydrogen is 1 times 2, that is 2, oxygen is what? 16. So if you add this together, that okay, everything times N equals to the molecular mass, which is 180. The implication of this is that 30N equals to 180. Therefore, N equals to 180 divided by 30. Therefore, N equals to 6. So that my molecular formula equals to empirical formula times N, and that is CH2O. My N is 6 times 6. So C times 6, that's 6 is 2 times 6, 12. O times 6, O6. So this is my molecular formula, and that is rightly glucose in this case. Moving on to the next question, that is 2008 question 43. We said this, the question says a hydrocarbon X with molar mass 26. So we have hydrocarbon X. In this case, you're basically saying that the molar mass of X is 26. That's according to the question. Consists of 92. When you say hydrocarbon, it is made up of carbon and hydrogen. It contains 92.3% of carbon. What is the molecular formula? Okay, if it contains 92.3% of carbon, then we were not told what is the percentage of hydrogen. So out of 100, carbon is already 92.3. So this is 100 minus 92.3%. 100 minus 92.3 is going to give us 7.7%. So looking for the mole of this will be 92.3 divided by 12, and this will be 7.7 divided by 1 because hydrogen is 1. Of course, this will give you 7.7. 92.3 divided by 12, that is also looking 7.7. So when you look at this, 7.7 divided by 7.7, 7.7 divided by 7.7, this is 1 to 1. So the implication is that the empirical formula is CH. That is the empirical formula. But in this question, we were not told to look for the empirical formula. We were told to look for the molecular formula. And we know that for us to look for the molecular formula, we need to calculate the number that cuts across. So in this case, we say empirical formula times N is equals to the molecular mass. In this case, my empirical formula is CH and equals to the molecular mass is 26. And when you look at that, carbon in there is 12. 12 plus hydrogen is 1. That's 12 plus 1 all times N equals to 26. So 23, N equals to 26, and therefore N equals to 26 divided by, equals to 13 divided by 13. So N equals to 2. Now that my N is equals to 2, my molecular formula is my empirical formula times N. So that is CH times 2. So this is C2, H2, and this gas in this case, this is looking, this is it, C2H2. This is ethane. This is ethane. This is the molecular formula, and that is ethane. Don't worry, when we get to organic chemistry, we get to understand this more. To 2008 question 43, the answer is ethane, and when you look at the option C2H2, that is option A. Option A is the answer, so that's gone. Moving on to the next question, and that is 2012. As you can see on your screen, question 44. 2012 question 44. If you look at this here is just similar to the question we took here for 2003 question 47. So look through the way we solved 2003 question 47 and use that to solve this 2012 question 44 displaying on your screen. Okay, it says 2013 question 50. 2013 question 50. Okay, when you look at 2013 question 50, it is also similar. Okay, it is also similar. We can as well liken that to 2003 question 47. It's something you should be able to solve. In case you're not able to solve, all you just need to do is visit us at 300plusacademy.com, link up with the WhatsApp group there, and of course DM the admin will attend to your needs. But for 2012 question 44 and for 2013 question 50, the processes are similar to what we've done for 2003 question 47. So moving on, we have another question on our hand, and that's going to lead me to talk about vapor density. 2015 question 23, as you can see displaying on your screen. What is the molecular formula of a compound with the empirical formula CH2? Okay, we're looking for the molecular formula. Empirical formula here is CH2, and we were given the vapor density as the vapor density in the question as 42. Need I say here that relative molecular mass, or what we call molar mass, is actually 2 is actually equals to 2 times the vapor density. This is a formula you should not forget, because when I want to calculate molecular formula here, my molecular formula is going to be empirical formula times n, and therefore I'll need my molecular mass to be able to do anything. So my molecular mass here is 2 times 42, and that is 84. Now that I have 84, I can then come and deal with things where I say empirical formula times n equals to the molecular mass. So this is 84 equals to, my empirical formula here is CH2. Carbon is 12. Hydrogen is 1. 1 times 2. 1 times 2 will give me 2. So that what I have is actually 14n equals to 84. Therefore, n equals to 84 divided by 14. And that way, n is going to give me 14 in 84 is going to give me 6. Now that I have 6, for me to get my empirical formula, my molecular formula is empirical formula times n. So my empirical formula is CH2 now times 6. So this is going to give me C6H12. That is my molecular formula. And if you look at the option displaying on your screen, that should be option A. That ends that. So 2015 question 23 gone. When you look at 2015 question 47, what we are being asked here, we've been given the empirical formula, we're going to look for the molecular formula, and we're given the molecular mass. This is something that is synonymous with what we've done for question 2003 question 47. Is something we can actually take care of. Okay, and last but not the least, let's look at UTME 1982 question 47. As you can see displaying on your screen, we have that 1 gram of an oxide of metal X. So which means we have an oxide of metal X. We were told in this question, as you can see, gave 0.80 gram of the metal when reduced with hydrogen. So for us to reduce this with hydrogen, okay, addition of hydrogen is actually a reduction. So in this case, H2O so plus X. So what it means is that this X has actually been reduced. 0.80 gram of the metal when reduced with hydrogen gave 0.80 gram of the metal. So it means this is 0.80 gram. 0.80 gram of X when reduced. Okay, and 1 gram of the, this was 1.00 gram before. So when it was reduced with hydrogen gas such that the metal now is alone, the metal X is alone, it's now 0.80 gram left. So which means that here my oxygen is actually 1.00 gram, take away 0.80 gram, and that means 0.20 gram. So what exactly do they want in this question? They want the formula of the oxide. The formula of the oxide, very simple. Okay, let this be X, let this be 0. Telling you they want the formula of the oxide here means they want the empirical. You can only get the formula using empirical formula. You get the formula of the oxide here using empirical formula, and that's something very direct. For X, okay, the mass was 0.80 gram, and for oxygen in the oxide here, the mass 0.20 gram. Of course, we were given at the end of the question that we should know, it's something we should know. Oxygen is 16. Oxygen is 16, and X we were told was 64. So this is 0.80 divided by 64. So we are going to try to compute this. This gives me 0.0125, and 0.20 divided by 16 gives me 0.0125 as well. The implication of this is that This is 1 to 1, and that means that the oxide is XO. That is the implication. So when we look at the various options we have there, option B is the correct answer. SO is the answer. This is just a case of applying empirical formula. And with that, we've come to the end of this topic, talking about the empirical and molecular formula. Like I always say, this is chemistry. We are preparing for an exam. We are preparing for UTME and the likes. But then there is a way as to how you prepare. You move from the simple to the complex. Next up on the list of things is going to be more concept in Avogadro's number. We'll be looking at stoichiometry, and we are going to be looking at limiting and excess reactant. When we have a good control of this set of topics, all of our calculations in chemistry is going to be a walk in the park. From myself and the entire team here at 300 Plus Academy, it is bye for now.